and go ahead and minimize.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning to all of you. This is our monthly get-together with an hour of training on ME Scope. This is Mark Richardson speaking. I also have Brian Schwartz in the room with me, so he's going to be our technical coordinator. And hopefully this broadcast is going to go out over the internet, and we will all share in this training together. So I have ME Scope on the screen here, and I need to get rid of
orange button at the top right. Right. All the way to the right.
There we go. All right. Little technical difficulty getting my screen arranged here. This is ME Scope, and I've opened it on a project that most of you should be familiar with. This is called the Jim Beam project, and it normally is under the Demos tab. So you can see I've moved the mouse up here and I've placed it on the Demos tab to open up the Jim Beam project. So you can see this one here. There's a little description of it, and I've got this project open already. Now under the Current Project tab, you can see the different files that are part of this ME Scope project. You can see there's quite a few structure models in this project. Yours may not have all of these different ones. And then there's a couple of data blocks. These have got FRFs in them. And so we're going to go through today. We're going to curve fit these FRFs. We're going to talk about the curve fitting methods in ME Scope. And then there's also some shape tables down here, which is where the results of curve fitting are normally placed when we save our results. So the best way to get started with any set of data is, first of all, to just inspect your data. So this data here, if I look up here on the caption bar for this data block, there's 99 FRFs in here. That's quite a bit of experimental data. You may take more. We're going to look at another project later on that has quite a bit more data in it. In fact, 720 FRFs. So let's just start with this data. I'm going to right-click on the window, and the first command that appears in the pop-up menu is called Center the Data Block Window. So I'm going to go ahead and execute that just so that we can inspect this data. Now on the left is the graphics showing me the FRF measurements, and we're looking at log magnitude versus linear frequency on the x-axis, log magnitude on the y-axis. And this is a common way that we look at our data. Over on the right is what we call the traces properties spreadsheet, or these are parameters of the traces. So if I scroll the scroll bar over here all the way to the right, I can see the properties of all 99 of these measurements. So the first column there is what we call the measurement number, the M-pound number. And that's used to set up the animation equations. Those M-pound numbers in the structure model, we set up animation equations, and we choose data from different measurements to animate different points and directions. We're not going to do that today. That's more of an introductory, but just as a quick review, those measurement numbers are very important. And we also use that column to select various traces. Remember, in ME Scope, if we select something, then we only operate on the selected item. In this case, it would be traces. And if nothing is selected, then we operate on all of the traces in this data block. The other thing to look at are, well, the second column here is visibility. Let me expand this a little bit. I'm going to click in the spreadsheet and hold down the Control key on my keyboard, and now I'm going to spin the mouse wheel. So this is a property of all of the spreadsheets in Emscope. If you hold down the control key, spin the mouse wheel, you can expand the display of the spreadsheet so that you can see the items that are in there a little more clearly. The other thing you may want to do is right-click on the spreadsheet, and down here is a command called Reset Column Widths. Sometimes the columns get moved around and so forth so that you can't see what's in them. This is just like Excel. All these spreadsheets work the same in Emscope. The next column here are DOFs. Now these degrees of freedom, or DOFs, in this case because of the FRF involving 2 degrees of freedom, or 2 DOFs, there are 2 numbers in there. The first number and direction we call the roving DOF, and then a colon, and then the second number behind the colon with a direction is called the reference DOF. So when we talk about single reference, multiple reference modal testing, this is the way we denote it in Emscope. We put reference roving first, colon, reference second. And if I look through this data, I can see that this is a single reference set of data because all of the measurements have the same reference. And that is 15Z, or minus 15Z, as the reference. So that's where one of the sensors during the modal test was fixed, not moved. The roving is where one of the sensors was moved for each measurement. So the FRF is what we call a cross measurement. Over here under input-output, you can see that this is designated as a cross measurement. That means that it's a measurement between 2 degrees of freedom, an input and an output. So this is kind of a MIMO designation. Multiple input, multiple output. Think of anything that you test as multiple input, multiple output. So every measurement that I make is either an input, an output, both. It can be an input and output if we're going to use it as a reference, or in this case it's a cross measurement. It's between an input point and direction and an output point and direction. So that's what we mean by cross. Under the units, you can see all the units are G's per pound force. Everyone else in the world would have G's per Newton. In America, we're still using the old English system. So we call it G's per pound, or we denote it here G's per pound. So these units are telling me that this data was measured with an accelerometer and some sort of a forcing function. And in this case, we used an impact hammer with a load cell on it. So we measured the force input and we measured the response acceleration due to the force input. So an FRF is a very special measurement. It's often referred to as a transfer function. Actually, a transfer function is more general purpose. FRF is a special case of a transfer function where the denominator units are always units of force. A transfer function in general, and Emscope handles them in different cases. Sometimes we call it a transmissibility if it's a ratio of, let's say, 2 accelerometer signals, or a ratio of any 2 signals. We call that a transfer function, or transmissibility if it's a ratio of the same type signal. We call it an FRF if it's a ratio of, in this case, response divided by force. Okay, so what are we going to do with this data? We can see that it's a good set of data. It's single reference. The roving transducer was a triaxial because we measured in the X, the Y, the Z, and then at 0.2 X, Y, Z, and so forth. So we measured triaxial responses in all points, and we measured the input at 15 and the Z. So I'm going to put this back where it came from, and I just executed that command again. The center, that just toggles between where it came from and the center of the screen, and I'm going to start the animation. Now I can do that in either window. I can start it over here in this window under Animate, Animate Shapes. So I'll start the animation. Now the animation is started displaying the data at the cursor position. You can see there's a line cursor over here in the data. And so that's what we call an ODS. That's an ODS there, or operating deflection shape of this structure. And we interpret that as if I had put in a force at 15 in the Z, which is the reference, this is how the structure would respond at all those different points. And there's 33 points. If I turn on I'm going to click over here and turn on the point labels. You can see there are all 33 of the test points on this structure. And there's additional points on this model, and we use interpolation for that. We're not going to get into that today. But we want to move on to curve fitting. But the first thing I want to do is just look at my data and see if it's reasonable. I want to go down here to the very low frequencies. If I put that cursor all the way at 0 frequency, or DC, you can see that this structure is hopping around a little bit. Well, the accelerometers don't work very well down there, so that's kind of what I expect to see. If I move it up just a little bit, though, now I see what looks pretty good as what I would call rigid body motion. There's a little bit of flex in the back plate there, and maybe a little bit of strange behavior over in one corner. But that plate is just essentially rigid body motion. It's bouncing on a soft structure that we use to test this thing. So here is another what I'd call a rigid body mode. We don't generally concern ourselves with rigid body modes, although they may be important to us, but we're more interested in the flexible body modes. And by that I mean when I go to this first peak here, as I sweep up in frequency, there is what I would call the first bending mode of this structure. The top and bottom plates are bending. There's a little bit of flex in the joints. These joints are just held together with cap screws. You can see the cap screws there in the model. This is a photo model of the actual beam structure. So there's the first mode. Now as I move this cursor, I expect to see mode shapes that I can recognize. There's a what I would call maybe a second bending mode. Now I'm just looking at one measurement here. Let me go and scroll to a different measurement. And now I can see that I actually missed a whole bunch of modes here. If I go back down here to this first peak, the advantage of FRF data is that if I see a peak in the data, that's evidence of at least one mode. So keep that in mind when we do the curve fitting. There is what I'd call the first mode of the structure, and that is a torsion mode of the back plate or the vertical plate. So we expect to see that. Now let me put the cursor on the second peak there, and there is the first bending mode that we looked at before. Now I'm going to go to this next peak, and there is another torsion mode. Now first torsion of the top and bottom plates as opposed to the back plate or the vertical plate. As I move this cursor along, though, you can see there's another mode shape right in here. We were there before. Now that is a complex mode shape because when I display magnitude data, the software gets the phase from the phase function. So it's actually displaying magnitude and phase. Let me put up the phase so we can look at that. I'm going to go over here under display the Bode plot. Bode has now got magnitude and phase. That's what we're looking at when we look at the animated picture. Now, there's an exception to this. If I display any other format except the real and the imaginary, then I'm going to see a magnitude and a phase together. So if I look at Nyquist, or in this case Bodie, I'm going to see a complex shape like this. Now let me switch it over to the imaginary display, though. Now I'm going to see a shape that's only using the imaginary data. And you see how that picture cleaned up? So with acceleration over force data, this is something that you want to keep in mind, that the imaginary peaks are a strong indicator of a mode of vibration. Now again, as I said earlier, we're looking at ODS data here, but when we put the cursor on a peak, the ODS is being dominated by a resonance. In this case, it's a second bending mode of the top and bottom plates. So if I'm just going to look at ODSs to see what mode is dominating my data, this is what I want to do typically, is look at the imaginary peaks. And even better, let's overlay them all, and that allows us to show, to find the peaks a little easier. So that's an even better way. Now if I click over here in the data with my mouse and I spin the mouse wheel, you can see that it expands the x-axis, or the frequency axis. So there's a good way to look at your data. And you can see that other mode there, that closely coupled mode, it doesn't have the amplitude, but it's there, and you can see all those peaks lining up. Now another thing to do when you're looking at your raw data, and this is all a prelude to curve fitting your data, is use the peak cursor, because your peaks may not line up as nicely as they're showing in this set of data. This data might be called textbook data. It's perfect. And you're probably thinking to yourself, well, I've never taken any data like that. My data doesn't look like that. Well, you should. You should, and we're not going to talk about it today, but you should spend the time to make the best measurements you can make. Because when you get to the curve fitting, you want to have data that looks like it's out of a textbook. Then the curve fitting goes easily, all the curve fitters work well, and all the answers agree from the different curve fitters. So just a warning that the time spent making good measurements is always worth it before you get to curve fitting. Now I'm going to turn on the peak cursor here, and I'm going to do that by clicking over here on this toolbar. And you can see that a peak, I've got a different cursor now, and what it's displaying is the peak value in the band. So I want to move that to one of these imaginary peaks, and if my peaks don't line up in my data, and there's many reasons why they may not line up. The common name is mass loading. When we have mass loading, the peaks are going to move around, but hey, we do the best we can when we're out in the field taking data. But the peak cursor is in Emiscope so that if I have data where the peaks move a little bit, I can still get a nice clean mode shape from that ODS data by using the peak cursor. Now here's the first step of curve fitting. I can go ahead and save that shape right now into a shape table. All I need to do, I'm going to right click over here, and under my tools menu, the first command in there is save shapes. So I'm going to do that, and I can start saving my shapes from the imaginary ODS data into a file, and I'll just call it imaginary peaks. And I've just done some curve fitting. Now, some people call this a poor man's curve fitting. You can do this in any Emiscope package. They all have that command in there, and you don't need to do any more than that. So now I can just go and animate this shape, and I'll just turn it on right here and say animate, and there's that shape that I just saved. So I've saved the mode shape. I've saved its frequency, 493 hertz. No damping, because we haven't really curve fit the waveform. We simply saved the imaginary peaks. But that's a good approximation of a mode shape. And I can go on here and go to another mode, and let's get this one right next to it, and I'll go in here and right click and go Tools, Save Shapes, and now I'm going to go and add this shape to my shape table of imaginary peaks. And I can come right back here and start the animation from here and animate the shapes. Now let me rearrange. I'm going to go up here to the toolbar. There's a command up here which I'll use a lot. It says Windows, Arrange Windows for Animation. Now I've got my shape table with my imaginary peaks below. I've got my FRFs above. If I click in either window, it will animate those shapes from that window. So I can go right here and click on the 460 Hertz, and there's that shape that I saved from the imaginary peaks. And I can do that, and I could, now that I have two animation sources, I can actually compare my FRF ODS data with the peaks that I saved. We'll get into a little bit more of that as we get into curve fitting. So let's go ahead now and do what we call curve fitting in Emiscope. A little more sophisticated. We can get, now we're going to curve fit this FRF data and get frequency, damping, and mode shape. I do that by going to the second command in the right-click menu, and that's called Modal Parameters. So here we are. We're into curve fitting now. It's still the data block, but you can see that it looks a little different. So in here, the first thing I'm going to do, I'll do a couple of things here. First, I'm going to change my format back, or my display back to magnitude. And I'm going to just display one at a time. I'm also going to unzoom everything. Now you can see there's some red lines in here. There's the peak cursor still on. I'm going to turn that off. This data is kind of low on the scale, so I'm going to press this button up here called Display Maximize, and that will raise it up there a little bit. And you can see up above I've got my data and some red line on it. That's called a fit function. Below I've got another function. We call that a mode indicator. Over on the right side I've got some tabs. Here's one called mode indicator, frequency and damping, stability, residues, and save shapes. So these are the steps of curve fitting that we're going to go through here. Okay, and I've already got some data down here in a spreadsheet, some curve fit data. You can see the frequency, the damping in two different units, well in the case of hertz, and also percent of critical damping, and then residue magnitude, residue phase, and something called modal participation. So we're going to look at all these different parameters. And but the first thing I want to do, you can see now that I'm in curve fitting, I've got a menu called curve fit. So I've got a whole new set of commands here that I can use for curve fitting. And the first one I want to use here is delete all fit data. I want to start with a clean slate. So let me execute that. And it says you're going to lose all your data here. You want to continue. Now all this curve fit data stays with the data block. You can see that when we opened up, it was already in here because someone else had already done this curve fitting and saved the data block with the FRFs and the curve fit results. But I'm going to start all over. So you can see I got rid of the red line up here, the fit function. I got rid of the mode indicator function below. And the spreadsheet over here is empty. Let's go back then to the mode indicator. Now mode indicator is used to find peaks in a set of FRFs. Remember when I was putting the cursor on the peak, I had missed some of the lower frequency modes because in the particular FRF I was in, I put it on the first peak that appeared in that measurement. So a mode indicator is used to scan through all the measurements and build up a function which will show me where the peaks are. We got two different kinds in here, CMIF and MMIF, and then multi-reference versions of those same functions. Not going to go into details of those. Let's go ahead and just say count the peaks. Now remember, we already saw that the imaginary part of the data is a strong indicator of a mode shape. So let's use that because those peaks are unique. There's one for each mode in the data. And now below you can see my CMIF using the imaginary part of the data. And it went through and used all of the data, all 99 measurements. And you can see that it's counted the peaks and it's found 10 peaks. So up here in this styler, or in this little number box here are 10 peaks. So some of the curve fitters in Emiscope require that you tell them how many modes are in there. In fact, all curve fitters require that. When we get to the stability diagram, you'll see that I don't know how many modes are in the data. I'll just start off assuming I don't know, and the stability diagram will indicate to me how many modes are in the data. So here we're just going to go ahead and count peaks. When we can do that, we can use a popular curve fitter in Emiscope called the polynomial curve fitter, and it works very quickly and it does a very good job on data that's nice and clean like this. So let's go ahead and do the next step. You can see that now that it's counted 10 peaks on the frequency and damping tab, it says 10 modes. So each peak is evidence of at least one mode. Now there could be more than one mode at each peak, and we'll look at a case where that's true. But I'm going to go ahead and push the frequency and damping button. It's giving me a little nag box here reminding me of what it's going to do to make sure that I want to do this. Do you want to continue? I'll say yes. So now I have frequency and damping for those 10 peaks. And you can see the damping again is in two different formats. One is the damping in hertz. We call that the half power point damping, or the 3 dB point damping, or the damping decay constant. The percent of critical damping is a ratio of essentially the damping in hertz divided by the frequency in hertz. Now it's a little bit more difficult than that, but that's a good approximation. The damping in hertz divided by frequency in hertz. This is called the damped natural frequency. Technically speaking, the critical damping, the percent of critical damping is a ratio of the damping in hertz divided by the square root of the sum of the frequency in hertz squared plus the damping in hertz squared. But you can see the frequencies are so much larger that the square root of the sum is really just the frequency in hertz. All right, a lot of words there. Now we're going to skip over stability. We're going to go right to the residues. What are residues? Well, it's as the name indicates, a residue is kind of a leftover or waste, or the remainder after we've done something called contour integration around a singularity. So there's some buzzwords. Basically what it is the strength of each of those peaks. It's the strength of the resonance peak, and you can see that each of the resonance peaks has a higher value. Some are lower values, and in this case we can't even see the one resonance peak because it's smeared by the other one. So the residue is going to give us the strength of each mode in each FRF, or a simple way to say it is it's the height of the peak, magnitude of the peak, value of the peak. So a higher peak, this one here is going to have a higher residue than one over here that's got a smaller peak. That's not technically accurate, but that's good enough for your understanding. I'm going to go ahead and push the button here, and again it says, do you want to continue? And now it's filled in the spreadsheet. Let me come over here. I'm going to click in the spreadsheet, hold down the shift key, and expand a little bit. And now you can see that the residues are filled in, both magnitude and phase. Now the curve fitter has to have that extra flexibility in it, that being the phase of the residue, in order to match the data up well with what we call the fit function. Now the fit function is the red line on the data. You can see the magnitude here. As I scroll through, the red line is laying pretty much on the data. So that's a necessary condition. If I have good modal parameters, then the red line is going to lie on the data. Now it's not sufficient though. It doesn't go the other way. In other words, if the red line lies on the data, that doesn't necessarily mean that I have good modal parameters. How do I know I have good modal parameters? Well, the best way is to save them and look at the mode shapes. So let's go ahead and do that. And then we're going to come back and we'll compare the answers from this curve fitting with some of the other curve fitters, and that's the other way to know whether I got good modal parameters. So in EmiScope, we have several curve fitters in here, and we use them all. Compare answers, compare mode shapes, compare frequency, compare damping. That's the only real assurance that you have that you're getting valid modal parameters. But having the red line lay on your data is certainly a necessary condition also. I'm going to go ahead and do that. Now let's just save these into a file called polynomial. So I didn't really go into all the details of the curve fitter. I'm not going to do that today. I'm just going to use them, and then we'll compare some answers. So here we got mode shapes, and let me go ahead and put I'm going to just put the data block down here, and we can go right ahead and animate them. And the other thing that I can do, and we'll go back and do that in a minute, I didn't even need to save them, but here they are. They're all saved from the curve fitting, and you can see they're all very, very nice mode shapes. Now again, your data doesn't look like mine, so you're going to say, well, that's easy for you to do. Let's go back and let me show you some more tricks that you can use to work on your data, which may not look like it came out of a textbook. So I'll stop this animation here, and actually I didn't stop it. I want to go to the draw, and that stops it. I'm going to go over here under Windows, and under Open Windows, this shows me a list of all the windows that are currently open for the different types of data files in EmiScope. So I've got my structure window that it's underlined because that's my current window. I want to open up the data block window again. Now I could have animated right out of here. Let me see if I can get everything up on the screen together. I'll put the imaginary peaks down. I'll put these down. And now I'm going to rearrange. Let me drag this over. This is another rule to remember. The last window that I touched will maintain its size when I arrange the windows. Okay, so here we are. I can animate directly from my curve fit results. So that's the quickest way to look at my results. And there it is. There's the first mode, animating right out of my curve fit results before I even save them. So we'll use this again. This is a more recent feature in EmiScope. You may not be aware of it, but I can look at the animation as soon as I finish the curve fitting. So that's a handy thing to do. All right, let's go back, and I'll stop that. I'm going to go up and execute that command again. That stops the animation. Many of the commands toggle on and off in EmiScope. I'll go back and make it large. Now let's clear everything again. So I'm going to go here. Here's that clear all command up on my toolbar. And I'm going to use the band cursor now. So I'll set the band cursor up, and I can use this polynomial method in small bands. So you may have some machinery running in the background, 60 cycle noise, a whole bunch of different things showing up in your data that you're not really interested in. But let's just say you're interested in those first two modes right there. That's all. I can expand the display here, so we'll just focus our attention right here. Those are the two that I care about. I can go over here and do the mode indicator. So I'll do that. There's the two peaks for that set of data. I'll do the frequency and damping. Let me do that. And then I'll do the residues. So there it is. I've just gotten estimates for those two modes in that frequency band. This is very handy for working with, let's say, data that's got a lot of stuff in it that you don't really care about. Kind of a divide and conquer approach. And we can compare these mode shapes with the previous ones, and we'll see the answers on this type of data are going to be very, very similar. Maybe a little bit of difference, but not much. Let me go ahead and clear that out and show you my favorite command in MEScope, and that's called the quick fit. So quick fit will take whatever method I've set up for a mode indicator, whatever method I've set up for frequency and damping, and whatever method I've set up for residues. You can see in this case I'm going to do CMIF, global polynomial, and polynomial. And when I hit quick fit, it will do all three of those and give me the results that I just did by carrying out each step. So there's quick fit. It's done. The nice part about that is now I can move my band cursor over and I can get these next two modes here the same way. So I can build up my shape table or my modal parameters table. This is not the shape table, but the modal parameters, by just going along and using the quick fit. Bingo, there it is. Quick fit actually found three modes. Remember, there was another mode in there that didn't show up in this particular measurement, but in some of the other ones it shows up. So quick fit those three. Now I can scroll across here, and now I can just, well, the band cursor is a little too wide. Let me set it around this guy. I'll just set him there and do another quick fit. And go across again. Here's three modes over here. I'm going to set my band around those three modes. You see, if I click inside the band, it moves the whole band. If I click outside, it moves one of the edges of the band. And I'll do another quick fit. And do I have any more modes? Oh yeah, here's one more over here. So where's my band? Now I can't find the band. The best way to find it is just turn it off, turn it back on, and it will show up right in the middle. And I'll do another quick fit. So there's 10 modes. Now how do I know whether those match up well with my data over the entire frequency band? Well, let me unzoom. So I'll hit the moves button. You can see I've got little red fit functions in those bands where I did the curve fitting. I'm going to turn off the band cursor, and I'm going to use a different command that will, and I want to unselect over here because I want to use all 10 modes. And now I'm going to use another command up here, and it's in my toolbar. It's, let's see, where is it? Right here. Fit function synthesis. So what that's going to do is build a fit function. And it went right off the screen. So there it is. I had to hit this maximize to get it back in the view. There is my reconstructed fit function using the modal parameters over here in the spreadsheet. So you can see that that's a pretty good result also. Okay. Got 15 minutes here. Brian's telling me to move along. So let me go to the next method, and that is the stability diagram. And we've already been able to count the peaks here in this type of data because they're all nice, clean measurements, not a lot of noise. The damping is very light, and the modes are nicely separated. So we can count the peaks, and all the polynomial and the quick fit work very well. But let's let's go use the stability, because that's when you have data that you just can't count the peaks very easily. And even if you work in small bands, you're just not really sure how many modes are there. So for that, we can use stability. Again, I'm going to clear out everything. And now I've got some different methods. There's 3 new methods in here. One called AF polynomial, complex exponential, and the Z polynomial, and then multi-reference versions of those. So let's just try the first one, and it's called AF polynomial. I'm going to go, and here, rather than have 10 modes in here, it says maximum model size of 50. So what that means is I'm going to solve the curve fitting equations for 1 mode, 2 modes, 3 modes, all the way up to 50 modes, and lay all those solutions on a stability diagram, and then we'll look at that, and from that we'll be able to determine how many stable modes we actually have. A stable mode is one that's going to keep reappearing on the stability diagram with the same frequency and damping within some tolerances. So let me go ahead and do that, and we'll look at the results. Okay, well, it's got some ugly colors here, red and green. Let me change those colors. I'm going to right-click and go to my data block options, and under contour colors, there's the red and the green. I'm going to change that second color to blue. Those first 2 colors are being used by the stability diagram to color what we call stable pole groups. Now, what's a pole? A pole is a pair of frequency and damping for a particular mode. So a pole is a frequency and a damping value for a mode. And we saw that we already got those values by curve fitting with the polynomial. This diagram here, the stability diagram, you can see underneath is the mode indicator that we used. We had that one before. And let me zoom in here and we'll take a look at some of these poles in the diagram. These are all the frequency and damping estimates that came out of the curve fitter. Now I'm holding down the Alt key on my keyboard, and you can see that it's telling me the frequency and the damping of each of these poles that it found by curve fitting this mode. And then over here on the left you can see the model size. So the model size started out way down here at in this case it didn't find anything with a model size less than 14. And now it's starting to find poles, and here's the red ones here are at 492 and 4.7. You can see that the damping is the horizontal bar and the frequency is the little vertical bar. So frequency is marked in the vertical. The damping, remember that damping in hertz, is the half power point damping, or the width of the resonance peak. And you can see here that here's 2 modes that are fairly close together in frequency. You might say they're closely coupled, but their damping is quite different. Now, we won't go into the discussion of why that's the case, but that's true in the physical world, that we can have 2 different modes that are very close in frequency, and their damping is quite different. Now, I'm scrolling here, and you can see the damping of these other modes that it found in the stability diagram. And the reason it's colored them all the same color is that all of these solutions here, for instance, let's just look at this column of blue ones here, they have all fallen within these tolerances up here: frequency tolerance, damping tolerance, and minimum number of stable poles. So all those answers that are within 4 hertz of frequency and damping, and there's at least 5 of them with that meet that criterion, those are all colored one color. And then these other ones over here, the red ones, the same thing. All these values are within the tolerance that we've listed up here. And I can tighten these tolerances or loosen them however I like. If we show the poles, let's go and put the poles up here. And then I'll zoom out so you can see them all. Now we're actually looking at what we call a pole diagram. Frequency along the horizontal axis, damping along the vertical axis. And you can see that the estimator here, the AF poly estimator, got the frequencies very close, and the damping is also very close. This axis is expanded here on our display, so you can see that the damping values are different, but they're all within the 4 Hertz tolerance. So that looks pretty good to me, except right here you can see that I've got 2 groups of poles. Some of them have heavier damping than the blue ones, are heavier than the red, but same frequency. Well, I know that there's, from my curve fitting, my previous curve fitting, that there's only one mode there. This is going to give me 2 modes if I save these results. So I want to go over here and increase the minimum number of stable poles and see if that doesn't get rid of one of these. So let me just move that up a little bit, and bingo. Now I've cleaned up the picture. You can see that for each of the 10 modes, and we actually have some rigid body estimates down here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 modes on my poles group. All those poles now have at least 8 poles in them that satisfy the frequency and damping tolerance. Now I can go ahead and say save the groups. And when I say save the groups, I'm going to get modal parameter estimates in my shape table, or in my modal parameters spreadsheet here for all of those stable groups. And you can see there's 14 of them. So I got too many, and so I need to get rid of maybe the first several here. These first 3 I'm going to delete because those are rigid body. I don't really care about those, so I'm going to delete them out of my spreadsheet. So let me go ahead and delete those. And I've selected them. Up here is another command on the toolbar called delete selected modes. Go ahead and do that. Now I've got 11. Oh, here's another one right over here, way out here at 1900 Hertz. That's what we would call a computational mode, because if you look up here in the data, there are some tails. That's here right in this measurement. You can see the tail of some higher frequency modes. Now, that can happen for 2 reasons. I either excited those higher frequency modes, but I don't really care about them, so I'm not looking beyond 2 kilohertz. Or I actually measured beyond 2 kilohertz and then truncated my data set to the 2 kilohertz. And in fact, that's what we did. We excited out to 3 kilohertz, but we saw some mass loading in the data beyond 2 kilohertz, so we just chose to ignore the modes beyond 2 kilohertz. But you can't completely ignore them when you curve fit, because you can see the influence of those higher frequency modes. And the curve fitters actually tried to curve fit these tails, and so that mode out there, that mode, that stable group, I want to remove that one also. So let's delete that guy. Okay, I've got a good set of modes here. I haven't been able to see the fit function, so I need to go over here with this. You can see I've actually got residues from this curve fitter, but in order to see the fit function, I need to press the residues button, or I could have gone up here and synthesized, which we did last time. So I could have gone up here and say synthesize, and there it is. It's giving me the same thing. So very good fit function. That's necessary if I'm going to have some good results here. Let me go ahead and save these, and we'll call this the AF poly method. Okay, there they are. We could go ahead and animate them, but let's do some more curve fitting before we do that. I'm just going to save all these results. Let's go back and let me switch back over here so we can look at our stability diagram again. And I'm going to clear everything out. And let's use a different method. Let's go under your methods and complex exponential. Let's try this method on the data. Now this is a time domain curve fitting method. Very traditional, been around for many years, used by many different people. It went in inverse Fourier transformed those 99 measurements, curve fit them in the time domain, which is called an impulse response, and then is showing me the stable poles estimates that it got. Now it's still got the same settings that I had from before, so it's already cleaned up the diagram quite a bit for me because I told it to give me at least 8 stable poles in each group. Here's another button, Show All. This is going to show you all the answers that it got before we filtered out the data using the stable frequency, the stable damping, and the number of stable poles. So that we use a filter. There's what the curve fitter actually gave us in terms of poles. Then you can see that it's quite a bit of stuff there. But if I turn the filter on and have the software process the data with these tolerances, I get a much cleaner result. Now again, we've got some rigid body modes. If I turn on the band cursor, in curve fitting we use the band cursor for not only curve fitting but for saving results in this case. So if I go ahead and save the stable groups, there I got 10 of them. Now I don't have residues with this method, so I need to go to my residues tab and push the residues button, and there it went ahead and curve fit in that band using the polynomial fitter. We used that one before, and you can see I got some very good results there. So let's go ahead and save those, and we'll call those the complex exponential method. Okay, one more curve fitter and under stability, and it's called the Z polynomial. Now this one is similar to something called Polymax. It's been documented by the competition, and it uses the Z transform in a frequency domain to curve fit the data. A little bit similar to complex exponential, but it's a frequency domain version instead of a time domain version. I'm going to clear out all the data. And let's go ahead and say stability, and there it is. Again, I used the same setup that I had from the AF Poly. You can see it didn't find as many estimates, but it found them in for all the, here's the closely coupled mode here is missing. So I'm going to drag this down just a little bit. You can see that it's got some estimates in there. And now I've got some stable poles for all 10 modes. I'm going to go ahead and save it. I got 11, so I got something extra in here. Not sure where it is. 454, I don't remember that mode.
228.
Oh, 228, okay. Let me see if I can see that on my diagram. Oh yeah, here it is right here. You see over here I've got a red group and a blue group. So I've got 2 groups here from this curve fitter, and I'm just going to go ahead and delete the 228. So I'll delete that mode. And let's go ahead. This one again doesn't get the residues, so we're going to have to get them. And there's the fit function. Looks pretty good. I'm going to save those modes, and we'll call them the Z poly. Okay, so I got a lot of curve fit results here. Now, one thing I could have done, you can see in the shape table, it's telling me within the label. Let's make this large so we can just look at these results. It's telling me the method that I used to get the frequency and damping, and then down here, I don't have the label.
Yeah, right there. The column you're on.
Oh, there it is. So I used the polynomial method. It just says poly in there. So these are abbreviations for the curve fit methods that it used to get down below the mode shapes, the residues, and it's called a residue mode shape. And all we did is save the residues for each measurement and each mode, and then up above the frequency and damping for those 10 modes. Let me look at all my data here, and I'm going to put down my model, and we'll put down the curve fitting, and let's get all of our shape tables open again. We've got the polynomial, we've got the AF poly, we've got complex exponential. Let's see, did I get that open? And let's arrange them all. So here are 4 sets of curve fitting results. Now I can compare any one set with another, or I could put them all together in one shape table, and then I can do what's called a MAC calculation, and that will compare all the mode shape estimates. I could also cut and paste the frequency and damping into a single shape, if you will. Remember, these spreadsheets work just like an Excel spreadsheet. I can cut and paste cells from one place to another. So I could put all the frequency and damping into a shape and compare those with the MAC calculation. I'm opening up here just some of the shapes so you can see them. We're kind of running out of time, but let's just go ahead, and I'm going to paste them all together in one shape table, and that way we'll be able to look at the results a little more easily. So I'm going to we'll take this polynomial table, and I'm going to take my AF poly, and under edit, I'm going to copy these shapes to a file, and I'll copy them into the polynomial, and I'm going to add 2. So I've added those 10 shapes, and you can see them here. Here they are over here. So I've got 20 in there now. Now I'm going to come down here to my Z poly, and I'm going to do the same thing. Copy shapes to a file, polynomial, add 2, and finally I'm going to put the complex exponential. So now I've got 30 shapes in there. I'll go down here to the complex exponential, edit, copy shapes to file, and polynomial, and add 2. So now I've got them all in one shape table. Let me just expand this so you can see the different methods. So we got 40 shapes in here. We got the complex exponential, the Z poly, the AF poly, and then up in the top are just the global poly. Now again, I've got something selected here, so I want to unselect. First thing we could do is simply look at all of the mode shapes. So let's do that. Display modal assurance. I'm going to compare it with itself. There they are. Now, all of these are very close to a value of 1. So what am I looking at here? Well, I'm looking at the diagonals are each mode shape with itself. The off diagonals are each group of 10 compared with the polynomial shapes. Now, if I put the cursor up, you can see the values are all very close to 1. Let's do it a different way. Let's let's select the first 10. I'm holding down the Shift key. So there's 10. Now I'm going to select, let's just go get the AF poly. So I'm going to hold down the Shift key and click on number 20. Let's just compare these shapes. So this is AF poly with the polynomial fitter. Now it's saying you've got shapes selected. You want to unselect? I'm going to say no. And I want to compare them with themselves. Again, it's the same shape table, but it's asking me the same question over. So here, the off diagonals are comparing the AF poly results with the polynomial quick fit, or in this case, we did it through the 3 steps. And the value of 1 is a very good result, and you can see that we've got a very good match here. So let's go back and see if we can now unselect, and I'll again select the first. Well, it's easier to start with the AF poly. Let me start with that, and we'll select all the way down here too. So we're going to compare AF poly with Z poly. Let's take a look at that. MAC value. Uh-oh. MAC value. So there they are. Now you can see that there's one here that dropped down to 94%. Still a good answer. That's comparing the AF poly with the Z poly. And since the AF poly compared well with the polynomial, we could indict the Z poly fitter as being the weak one here. But even there, you can see the frequencies are 454 versus 460, so we're off by 6 hertz on the frequency. Now that's not our stability tolerance, that's the curve, that's one curve fitter versus another. Didn't get the frequency, the Z poly didn't get it as close as the AF poly. Okay, so let me go back here again. I'm going to close this, and let's just try something else here. I'm going to select these first 10. Now I'm going to come down here, and we're going to get the complex exponential. I can't hold down the Shift key to do it, but I can simply go along and click on them one at a time. Now it's scrolling me back to the top. Okay, so now I've got, if you can see that, I've got the first 10 and the last 10. And I'll compare their mode shape. So this is the polynomial versus the complex exponential. MAC value, polynomial. There again, you can see the MAC values are very good. I think the worst case here is this one, 98% at the 1500 hertz mode. All right, well, we've compared these different curve fitters. We didn't get to the multiple reference. We did all single reference curve fitting today. Maybe next month we'll get into multiple reference curve fitting and show you how those other curve fitters that we didn't cover today will do multiple reference curve fitting if we have that type of data. We haven't received any questions, Brian is telling me. You can email questions now, and we'll spend a few minutes answering any questions that you may have via your email, and we'll answer them on the air here.
Yeah, there's a questions area on the panel. Open up your panel, top left. So if you go down to the questions, there's a questions tab there. So that's where they'll come.
There's no questions. All right, well, we're going to sign off, and that's the end of our discussion today, and hope you have a good day wherever you are.